Now it's time to learn another mathematical tool to put in your toolbox, which we'll call the Laplacian. So the Laplacian is a tool that you can apply to a scalar function. And to explain how to use it or what it exactly means, let's continue to use what we're going to apply to, the electric field and the charges and the potential. Let's start by reviewing the basic quantities that we use in our description of electrostatics. Let's stick with a kind of a parallel plate-like geometry because we're already in a groove and we're used to thinking about it. So let's continue using that to come up with our expressions. Let's say we have a bunch of positive charges and a bunch of negative charges over here in a parallel plate-like geometry. And in this case, I'm going to use volume charge density, even though in the way I'm drawing it is a little bit more like a surface, but this is just to keep the drawing clean and simple. One of the first quantities that we talked about is the charge, right? So a charge, let's not forget, is like an arrow generator or an arrow drain, right? If it's a positive charge, then it generates arrows. If it's a negative charge, then it sucks in arrows and eliminates them. Right, so it's kind of like an arrow faucet. So these positive charges generate arrows, and then let's just use a different color. These positive charges generate arrows, and these negative charges take in arrows. Right, so you can think of it as positive charges are arrow faucets, negative charges are arrow drains, and it flows from the faucet down into the drain. And these lines, these arrows that come out as a result of that, is our electric field, right? And then once we have these electric fields, we know these are vectors. In a way, these can be viewed as slopes. So these slopes that go from this value down to over to this value over here. And so if you think about it some more with these slopes, you can also create the elevations that arise from these slopes, and that gives you the potential, right? So we have the potential, which is like the elevation, and the electric field, which is kind of like the slope or the downhill slope arrow. So if you had a topographical map, V, the potential is the elevation, E is kind of like the arrows that signify which direction is downhill. And then rho V doesn't really quite fit into the topological analogy quite as well, but they're basically the generator or destroyer of these downhill arrows that show up. And with this, we have the calculus relationships that allow us to move from one to the other, right? When we talk about the potential, relating the potential or the elevation to the electric field, which is the slope, we have that the electric field is going to be minus the gradient of the elevation, right? So this negative sign is because when you take the gradient, you're given uphill arrows, and the electric field is defined as a downhill arrow going from a positive charge to a negative charge. So you have this negative sign here. And then separately, how do we relate the electric field to the arrow generators? Right, it's a little bit of an indirect. What we want is the electric flux density, right, or epsilon E, which is going to be equal to D. If we have that quantity, the divergence of the electric flux density gives you the amount of charge density related, right? So what we want to do with the purpose of the Laplacian is to allow you to relate the potential to the arrow generator or arrow sink. So relate the potential to the charge density. And so as you can imagine, since they have kind of like a vector version of a derivative relationship going from one to the other, you can think of this as the second derivative application, right? So if this is if the quote unquote derivative of this gives you that, and the quote unquote derivative of this gives you the electric field, then the second derivative like operation should give you rho V. And that's the framework where I want to introduce the Laplacian. Is you can think of it as the second derivative operator that allows you to tie the potential to the volume charge density. So let's starting with these two equations here, we can write that the divergence of epsilon and we're just going to go ahead and plug this into, we're going to plug the epsilon E into the electric flux density and also plug this definition into E. So you're going to have epsilon minus the gradient of V is going to be equal to rho V. And moving some things around, you have minus epsilon is going to be equal to the divergence of the gradient of V, which is rho V. Subtracting this over, you're going to be left with this divergence of a gradient nonsense with a negative sign over there. And then I think we've simplified this as much as we can. So to make this prettier, we just simply define this as a new operator. So we define the Laplacian, which is the divergence of the gradient of a function. And we're going to use this del squared to describe that. So plugging in this notation, you come up with a pretty result that the Laplacian of the potential is going to give you minus rho V over epsilon. And that is Poisson's equation. It sounds like a lot, but basically what you're saying is, again, since you're saying that since the divergence of this gives you rho V, and the gradient of the potential function gives you E, therefore the divergence of the gradient of V is going to give you minus rho V, and then you have this epsilon here that relates from the fact that this is the divergence of D. So that's Poisson's equation. And in the case of if there's no charge in the location of interest, so you would need to use this equation if you're trying to evaluate the potential over here. But if you're just sitting in here, if you're just sitting over here where there's no charge and things are going well and you're just humming your little tune, then this quantity is going to be equal to 0. And that's what people refer to when they say Laplace's equation, where the Laplacian of the potential is going to be equal to 0. And so the nice thing about this equation is that this is actually something that you can numerically integrate. And usually if you're given a problem and you need to find out what the field is or the capacitance or this, that, or the other, usually what the information you have is the potential and the boundary conditions. So if you can numerically integrate this, if you're given the potential at all the different locations and where the charges are, and you have a numerical technique that allows you to do integrations, then you're able to use that to figure out the electric field everywhere and basically solve for what's going on electrostatically in the region of interest. So the task remains is to define the Laplacian for the different coordinate systems. So let's write that out next. So the Laplacian of any, remember this has to be a scalar function. The Laplacian of a scalar in Cartesian coordinates is basically what you would expect. So remember, we kind of had the notation that this del parameter is like dx x hat plus dy y hat plus dz z hat. And if we define it this way, the kind of operations that you would have work out nicely in the case of Cartesian coordinates, but maybe not so much for cylindrical. So in Cartesian coordinates, it's as you would expect. It's simply the second derivative. In cylindrical coordinates, you have to make some adjustments, some normalizations, kind of like how you would have had to in the calculation of the divergence and the gradient. 1 over rho squared. I will just write this out so that it's presented at a reasonable speed for you to digest. And then finally for cylindrical coordinates, as is befitting of cylindrical coordinates, it's usually the most painful. So you have 1 over r squared d by dr, and you'll see some similarities with your formulas of how to do gradients and divergence in these coordinate systems. And the important thing to note here with these formulas, again, I don't think it's necessary to really hack through this, maybe just one time to really feel like you have an understanding of it. But it's important to know how to apply it. And the main trick is that you need to make sure that you apply it in the correct order. So in this case, make sure you take one derivative first, and then you multiply it by sine theta, and then you take another derivative. So work your way for each term, work your way from the right side back out through the terms in the left side, and take the derivatives when you're supposed to, combine terms when you're supposed to, and don't jump the gun and do it too early. And so that's the Laplacian. Again, as a quick review, it basically relates. It's a second derivative-like term where remember we had these three quantities that are kind of related by vector calculus versions of a derivative. So a divergence of the electric flux density gives you rho v, and the gradient of v gives you e. So the Laplacian is like a second derivative that allows you to relate v to rho v. And that's important because quite often this kind of integrating this kind of a tap, this kind of an operator, is something that you can do numerically. And the potential is usually the description that you're given of the situation that you're trying to solve the electric field for. And so this is the numerical way to solve this differential equation, to solve the Laplacian, is actually one of the key tools that you use to solve things with a computer when pencil and paper doesn't quite work out. And we'll do simplified versions of using this operator to solve for the electric field, which I'll tie together in our next discussion. And one final motivator that I'll throw out there for your working with this kind of math that we haven't really dealt with in electrical engineering, at least prior to this class in some situations, is that these operators, the divergence, the gradient, the Laplacian, actually come into play for many physical phenomenon that you use in other disciplines, like in mechanical engineering and heat and mass transfer. You also run into these operators. And so having some kind of comfort level with this will also help you if you suddenly need to dabble in another discipline in order to get your work done, or if you need to collaborate with people in other disciplines. These mathematical toolboxes are really help out and can broaden the scope of people and topics that you can work with.